Once upon a time, there was a mountain. On the mountain, there was a temple. In the temple, there was an old monk telling stories to a young monk. And what was the story about? It was, once upon a time, there was a mountain. On the mountain, there was a temple. Such a story cannot go on endlessly. We always believe that every story should have a beginning. So, what should the beginning of our universe look like? And what happened before that? In this section, let's talk about the Big Bang. For your own identity, your origins and growth are indispensable parts of your story. You know very well how you came into this world, which gives you confidence that you are a normal person within the flow of history. But for the universe, that's not the case. Our universe is thought to have appeared about 14 billion years ago. Scientists know that shortly after its birth, the universe experienced the Big Bang, but they have limited understanding of the exact moment of its birth, the reasons for it, or what came before. Science can answer many questions, but it also has its limitations. Scientific theories must make predictions and be verified through experiments. If a theory cannot be tested experimentally, it falls into the realm of philosophy, religion, or speculation. For instance, someone might claim that a tiny pink dwarf exists floating between our galaxy and the Andromeda galaxy. Since this claim cannot currently be tested by science, it doesn't belong to the domain of science. Throughout history, many theories have made the leap from non-science to science. For example, the idea that matter is made up of tiny particles existed long before science had the tools to detect atoms. Similarly, the study of the Big Bang has transitioned from pure speculation to a scientific field. After all, studying events from 14 billion years ago is no easy task, especially since we cannot recreate the Big Bang. Fortunately, the Big Bang left behind many clues for us to verify and analyze using existing theories. The idea of the Big Bang emerged in the early 20th century when scientists discovered that all galaxies are moving away from us, indicating that the universe is expanding, a phenomenon known as Hubble's redshift. Using the equations of general relativity, it was found that this expansion could be traced back to a single point. The entire universe was once contained in a point of immense mass and zero volume, with infinite density. Initially, Einstein didn't believe that the universe could have originated from such an explosion. To avoid the conclusion of an expanding universe, he introduced the cosmological constant into the equations of general relativity, later admitting this was a mistake. The process of expanding from this tiny point to the vast universe we see today is what we call the Big Bang. Many people have heard of this theory, but they often imagine it as a bomb-like explosion, assuming that all matter was concentrated in a very small space before the Big Bang. Afterward, all the matter spread outward, traversing the entire space, and formed the universe we see today. In reality, the Big Bang was far more complex than this simple description suggests, containing many mysteries that remain unsolved to this day. Let's explore them one by one. The first mystery, quantum gravity. Our universe was once an extremely tiny point. Everything we see in the world today coexisted in that single location, compressed into a zero-volume point. This concept is supported by general relativity, but it also reveals a peculiar truth. At the smallest scales, the universe is a strange place governed by counterintuitive quantum phenomena that operate probabilistically. When mass becomes extremely dense, the effects of quantum mechanics become pronounced, causing the predictions of general relativity to break down. General relativity applies to large masses and expansive spaces, while quantum theory governs situations with extremely small masses and spaces. Under normal circumstances, these two theories do not interfere with one another. However, in the early universe, they come into conflict. Since we lack a unified theory that combines relativity and quantum mechanics, we cannot accurately predict the universe's earliest state. The second mystery: why is the universe so vast? If we simply view the Big Bang as an explosion starting from a single point, another question arises: even if the universe began as an infinitesimally small point or a quantum patch, why did it become so enormous? To understand this, we first need to grasp the concept of the observable universe. Your field of view forms a sphere with you at its center. Light from distant stars travels across vast distances to reach your eyes, and this journey limits the extent of the universe we can see. Over time, we can observe farther regions of the universe as photons take more time to reach us. Meanwhile, the matter within the universe continues to move away from us. Fortunately, nothing in the universe can exceed the speed of light, which allows our field of view to expand steadily and reveal increasingly distant regions. However, this brings an intriguing thought: if our observable range eventually surpasses the entire universe, what would we see? It suggests that we might observe regions beyond the stars, areas devoid of celestial bodies. Yet, for now, no matter which direction we look, we cannot see the end of the starry skies. The universe remains larger than our observable range, even though it is already 14 billion years old. Our mysteries are not yet fully unraveled. The third mystery is that the universe is remarkably smooth. At first glance, the universe might seem overwhelming and chaotic, but it also exhibits a consistent and uniform side. We can observe this uniformity in the cosmic microwave background, CMB, radiation. Let's use an example to illustrate this paradox. Imagine you're hungry and decide to heat a snack in a microwave. We know that microwaves heat food from the inside out. After a few minutes, the center of the snack becomes very hot, while the outer layer remains cooler. Now, imagine measuring the temperature inside this snack. If you were at the very center of the snack, you'd find that the temperature around you is uniform. However, if you were closer to the edge, you'd notice that the side near the center is much hotter than the side closer to the surface. You can do something similar with the universe from Earth. We can measure the temperature of the cosmic microwave background photons hitting one side of the Earth and compare it to the temperature of the photons hitting the opposite side. The result is astonishing. No matter the direction, the temperature is the same, approximately 2.73 K. It's highly unlikely that we're at the exact center of the universe, so the only logical conclusion is that the entire universe has roughly the same temperature. In other words, instead of being like a snack fresh out of an explosion, the universe is more like a well-prepared bath that's been sitting long enough to reach a uniform temperature. To understand what this phenomenon means, we must first realize that the photons in the CMB show us the earliest pathways of the universe. The early universe was much hotter and denser than it is today. Back then, it was so hot that atoms couldn't even form. All matter existed in a plasma state, a sea of free-floating ions and electrons. The energy levels were so high that electrons moved too quickly for atomic nuclei to capture them. However, as the universe cooled, things began to change. Once the temperature dropped sufficiently, the charged plasma turned into neutral gas. Electrons started orbiting protons, forming various atoms and elements. During this process, the universe transitioned from opaque to transparent. In the plasma state, photons constantly collided with free-moving electrons and ions. But once electrons and protons formed neutral atoms, photons were no longer significantly affected. At this point, photons could travel freely to other parts of the universe. For these photons, what was once a foggy universe suddenly became transparent. The universe has been cooling ever since, and most photons continue their journey undisturbed. The photons we measure in the CMB today are these same ancient travelers. The strange thing is that their temperature appears uniform in all directions. Wherever you look, the photons have the same energy. The CMB is extraordinarily uniform, like something that has been thoroughly mixed over a long time to reach equilibrium. For instance, if you let your snack cool for a long period, its temperature would also become uniform, with all the molecules reaching roughly the same temperature. But these photons in the universe are incredibly old. They appeared not long after the Big Bang, making each one an elder at 14 billion years old. From one direction in the sky, you might see a photon that has traveled an immense distance to reach your eye. If you look in the opposite direction, you'd see another photon just as ancient, coming from an equally distant place. So, if these photons come from opposite ends of the universe, how could they have the same energy? How did they have the chance to interact, mix, and exchange energy? For them to have interacted enough to reach the same temperature, their communication speed would need to exceed the speed of light. All these questions lead us to one answer, and that answer is called inflation. End part. As we've seen, the universe's vastness and uniformity raise many questions. The mysteries of its origin, the Big Bang, and its continued expansion are just the beginning of our journey to understanding. But for now, the universe remains larger than what we can observe, leaving us with many unanswered questions. Stay tuned for part 2 of this episode, where we'll explore the mind-bending theories behind what happened before the Big Bang and the possibility of multiple universes.